In this video, we are going to solve problem 7.3 from the book. This involves solving for internal forces and bending moments. So the problem gives us that alpha is 90 degrees, asks us to find the internal forces at point J, which is this point right here. And we're going to go ahead and assume that we're in equilibrium and that the system is weightless. I started this problem out by drawing a free body diagram of the problem. So we replaced the cable at C with that tension force. We replaced the pin at B with a BX and BY force. And then we have that downward 780 Newton force. So I can solve this problem. First, I should write what theta is. So theta is equal to the tan inverse of, if we look back at our dimensions, it's going to be 480 plus 240 is the opposite. 240 plus 480. That's going to be divided by our adjacent, which is 300. If I do that calculation, I get that the angle theta is 67.3 degrees. Once I have that angle, I can write my three equilibrium equations for this free body diagram. So I can sum the forces in the x direction. It's equal to 0. So I have bx plus t cosine of 67.3. If I sum the forces in the y, I have that's equal to 0, by plus t sine 67.3 minus 780. And if I sum the moments about some point, let's choose point B. It's equal to 0. I have the x component of t. So that's going to be t cosine of 67.3 times my moment arm, which is going to be that 240 plus 480. So that's going to be 720. That x component is going to make us rotate counterclockwise about point B. So that will be a positive moment. Then I have the y component of t sine 67.3. The moment arm for that, looking back at my diagram, is going to be 300 plus 300. So that will be 600. That upward y force is going to make us rotate clockwise about point B. So that's going to be negative. And then I have that downward 780 Newton force, so 780. The moment arm there is going to be this distance here, which from our drawing is 300. That's going to make us rotate counterclockwise, so that is going to be positive. I can use these equations and solve for t, bx, and by. And I get t is 849 newtons. Bx is minus 328 newtons. And by is a minus 3 newtons. So that's it for finding my external forces. Now I'm ready to start looking for my internal forces. So here I've drawn or started to draw two free body diagrams. So I have separated the rigid body into two separate sections, and the separation of those sections is at J. So at J, for both of these sections, we're going to have our normal force along the member. So let's call that normal force. We can call it F. It's going to be along the member there, F. I'm also going to have a shear force. So I'm going to draw my shear force here, V, and I'll have an equal and opposite shear force in this drawing, V. And then lastly, I'm going to have a moment on each of these members. So I'll draw the bending moment here, going that way, and my bending moment here going the opposite way. Now I don't need to draw both of these free body diagrams. I just need to draw one of them, and I can use either free body diagram to solve for my unknowns. To write my equilibrium equations, I'm going to use the free body diagram on the right to solve for those internal forces. So I'm going to use this free body diagram here. I'm going to start by summing the forces in the x direction. So I will have Bx, which I solved for previously. And then let's just do a little trig here. For my F force is going this way. My V force, shear force is going this way. And those are 90 degrees from each other. So we have a 90-degree angle. Previously, we've solved and seen that this angle here is 67.4 degrees. And that this angle here is going to be 90 minus 67.4, or 22.6 degrees. So continuing my equation, I have Bx, then I'm going to have minus F cosine of 67.4 minus V cosine of 22.6. I'm also going to sum the forces in the y. So here I have By minus F sine of 67.4 plus V sine of 22.6. Lastly, I'm going to sum the moments about some point. Remember that if I have a point moment like this, the moment is the same everywhere. So I could take the moment about any point on this free body. I typically prefer to take the moment about the cut or the moment about this point J that's of interest. So I'm going to take the moment about point J. So I've drawn that bending moment here in the negative direction. So I'm going to write negative M. And then I have the moment caused by Bx. So that's going to be a minus Bx times the moment arm of 480. And then I'm going to have plus By times the moment arm of 300. Remember that the values for Bx and By are both negative, so when I plug into these equations, I'm going to have negative M minus, and then I have to plug in that negative value that I got previously, minus 328 times 480, and I have plus By was a negative 3. I just realized that I had an error here with my moment arm. So it's not 300. 300 is the total distance from here to here. And I need instead the distance from B to that point J. So I'm going to erase that. Let's draw a similar triangle here. Here we have point J. This is point B. we have 480, 240. This distance here is 300. This distance here is x. If I solve for x, I get that it is 200. So that moment arm there should be 200. So then I can plug in 200 right here. And I solve and I get my bending moment is 156.8 Newton meters. I can also use substitution to solve for my other equations, solve for V and F. And I get F is minus 129 newtons. And V is going to be a minus 301 newtons. So that those minuses there mean that I drew the forces in the wrong direction. So F is actually going in the opposite direction and V is going in the opposite direction as well. So that's our first example of solving for internal forces and bending moments of rigid bodies.